Welcome everyone to today's lecture presented at the NFC Institute of Engineering and Technology, and I am Hasan Khalid. Today I am going to discuss the Chapter 5 State Space Analysis from Discrete Time Control System by K. Ogata. Today, the content that is being covered in today's lecture is the concept of the state space model, the state space representation of discrete time system, along with the different standard canonical forms, including the controllable, observable, diagonal, and the Jordan canonical form, along with the examples. Now, first of all, let's discuss the concept of state space. State space method is basically used to represent the whole system into the formation of mathematical equations. The method of describing the system equation in the first order differential equation, or it has the first order difference equations. Then they are arranged to form the vectors that are representing the form of the matrices. I hope that you are well aware of the linear control system in which you actually form the state space equations where the A, B, C and D were the vector matrices. The main advantage of using this approach is to simplify the mathematical representation. The users have direct access to the input states as well as the output states. It also allows the engineers to design the control system with respect to the predefined performances. The state space can be carried out in the set of the inputs. Either the system can be MIMO, which is multi-input and multi-output, or it can be CISO, having only single input and the single output. And after that, when you actually represent the whole system, it actually appears as this form, where x of t is representing the first order difference equation, where a, b, c, d are the time varying vector matrices in this equation, and u of t is the time varying input, and t is the state of the. Now let's discuss the components of the state space equation. What is state? The state of the dynamic system is the smallest set of variables with the knowledge of these variables at any instant of t defined by t naught, and together with the knowledge of the input at these instants for the same time interval, completely determines the behavior of the system at those defined intervals or instant that were already defined by t equal to or greater than t naught. Now, the state variable. The state variable of the dynamic system is the smallest set of variables which defines the state of the dynamic system. If the system has n variables, then there will be n state variables starting from x1 and ending at the xn. These are all the variables that are used to describe the complete system. For example, if we have an RLC circuit and there are two components that are storing the energy, then there will be two state variables. One will be the current and other one will be the voltage, and they will be defined according to the conditions. The state vector. If n state variables are needed to describe the system, then there will be a vector with the dimension n, which is called as the state vector x of t. It determines the unique state of the system. Now next term is the state space. It is the n-dimensional with the axis consisting of all the state variables starting from the x1 to xn. They are called the state space, sometimes also termed as the state space model. Now state space equation. The equations that representing the input, output and the state variables together are called as the state space equation. Now let us represent the general state representation. Now this term is actually known as the state equation, where we have defined the first order differential equation x dot of t, that is equal to the axt plus bu of t, and the output equation is termed as the y of t, that's equal to the cx of t plus du of t. Now these two equations are responsible to define the dynamic equation of the whole system, where you actually get information regarding the output for the given input. Now keep in mind that this equation is involving the x of t, where t is the telling the state. Now if the system has a matrix A, B, C and D in term of the defined time interval, then the system is actually termed as the time varying system. However, in this representation, these matrices A, B, C and D are constant and are not varying with respect to the time. So the system can also be termed as the linear time invariant system or the LTI system. Now let us define these whole terms, where x is the state vector, x dot is the derivative of the state vector, u is the input vector, y is the output vector, a is the state matrix or also known as the system matrix, b is the input matrix that will be providing us information regarding the number of inputs, whether they are CISO or MIMO. C is the output matrix that will be giving us the some information regarding the how many outputs of the system are being having, either they are also single output or the multi output, and D is the feedback matrix. Now let us define the state equation for the discrete time system. Now in the previous chapters, especially in the first, second and third, we were given the information that if we are considering the discrete time system, then we will be replacing the t instant with that of the k. And since it is also known here that this vector is the first order difference equation, so we will be placing over here x k plus 1, which is equal to g of k x of k plus h k and u of k. Similarly, the output of the system has been written as the c k as x as a function of k plus d as a function of k and the u as a function of k. Also, it is to be noted that the system is time varying system because the information being conveyed over here as are all varying with respect to the instant k, g of k, h of k, c of k and d of k. Now if the system is assumed to be linear time invariant, then these variables k will be removed. Now similarly, also we can also define these variables here as the xk, which is a state vector as previously discussed, yk is the output vector, u of k is the input vector, g of k is the state matrix, hk is the input matrix and ck is the output matrix, and lastly d of k is the direct transition matrix. Alright, now let's look at the role of the variable k. The variable k, as it is being appearing in the previous slide, it implies that the matrices are time varying. If the variable k does not appear explicitly in the matrices, they are assumed to be time invariant or constant, just like the LTI systems. Now if I assume that the matrices G, H, C and D are time invariant matrices, then I would have to make them independent of the time instant k. So the final simplified version will be written as in the following way: g x k, h u of k, c x u of x k, and the d u of k. In our upcoming examples and this subject, we will be keeping our focus on the time invariant systems. Now let us draw the comparison between the block diagram of a continuous and a discrete system. In continuous system, the state vector is actually the x of t, whereas in the discrete it is been defined by the x of k. And also in the continuous domain we use integration, and in the discrete domain we use the z transformation. Now if you want to convert the continuous time signal into discrete time values, you need to add the sampler, and to hold those values you actually use the sampler and hold mechanism, or you actually imply the zero order hold or the first order hold for your requirement, but for converting all those uh, discrete pulses into the set of the continuous staircase values. The output state in the continuous is once again the x of t, whereas the output state in the discrete system is x of k. And similarly, the both of system have the some common boxes, just like c vector, and this in both of them are same. The feed forward path like the d vector is also same, whereas the input in the continuous time system is been mentioned as the b, whereas in the discrete time system we actually transform all those input analog values into the set of the pulses and replace that vector with the h vector. And similarly, our system in the discrete domain is defined by the g vector, and both of these equations for the state equations for both the system are also been mentioned in front of their block diagrams. You can easily see them. Now let us define the state space representation for this discrete time system. There are many techniques to represent the state space model for the discrete time control systems. And keep in mind that there exist n state space equation representation for a single system, but all of them will have a same transfer function. If the system is continuous, then it will have the same transfer function for the different state space models, and if the system is mentioned in the discrete domain, then it will have the same pulse transfer function for different state space models. Now consider the system that is been described by the following chain for the output to the input side, and by applying the z transform theorem we can easily form the general representation of the pulse transfer function, where y is the output and u is the input, and which is equal to the coefficients of b naught zn plus b1 coefficient multiplied by zn minus 1 up to the n variable of the coefficient b divided by the zn plus first coefficient of the a multiplied by the zn minus 1 and sum up to the last coefficient of the a. Now there exists the standard representation of these state space models. Generally there are four canonical forms, and the canonical form are actually the standard formation of these state space models: controllable canonical form, observable canonical form, diagonal canonical form, and Jordan canonical form. Now let us discuss ahead how these state space models are represented in each of the four canonical forms. Now in controllable canonical form we will use the pulse transfer function as a reference, and we will try to arrange their coefficients of the numerator and denominator to form our controllable canonical form. Now this state equation is actually representing all these states from x1 to xn in first order differential equation, and it's actually equal to the, this matrix is the G matrix multiplied by the state vectors from x1 to xn plus the inputs vector multiplied by the u of k. Now if you observe this vector G matrix, you can easily place those variables from the characteristic equation of the given impulse transfer function by placing all those coefficients from a1 to an in reverse negative direction. If it is starting from a1, a2 and till the an, we will be arranging those values in the negative in the reverse order from minus a1, minus a2, minus a3 and till the minus an, which is the last coefficient of the characteristic equation. Now if you look at the numerator of this pulse transfer function where the coefficients are b0, b1 and till the bn, you can easily write the output matrix that was C in the continuous domain and C as in the discrete domain as well. And the general formation is as follows: by starting from the bn, which is the last term of the numerator, minus the last term of the denominator coefficient multiplied by the value of b0, and in the next column the next iteration will be bn minus 1 minus the an minus 1 part multiplied by the coefficient of the b0 and so on till the first coefficient of the b1 till it arrives. Also keep in mind that the order of this whole system is defined by the characteristic equation power n, z raised to power n. If it is equal to 3, the order of this whole matrix will be 3 as well, 3 by 3 and so on. And similarly these coefficients will also be arranged accordingly according to the order that is being defined by the characteristic equation. While the rest of this arrangement is same as that of the conventional method, this is the d vector which is b0 multiplied by the u of k. If there is a feed forward path, then it will be considered. If there is no feed forward, then it will be assumed as 0. Now if you have understood how to write the controllable canonical form, you can easily write the observable canonical form if you keep in mind the following hint. If you want to write the G matrix of this observable canonical form, you have to take the transpose of the G matrix of the controllable canonical form. Now if you look at this previous slide, and keep in mind, if I take the transpose of this whole matrix, what will happen? It 0 1 0 up to 0, if it is the first row, it will be transformed into the first column. Similarly the second row, if I take the transpose of it, it will be converted into the second column, and all these last row will be appear in the last column. That will be my new observable matrix for the G. Now just take it a final look. All my last row after taking the transpose have been transformed into the last column, and similarly just by taking the transpose of the controllable G matrix I can obtain the observable G matrix. And if I need to write the output matrix C for the observable canonical form, I need to take the transpose of the H controllable matrix. If I take the transpose of this, I will get the output matrix for the C. Now just take a look back. Now this was my H for the controllable canonical form. If I take the transpose, what will happen? It will become a horizontal row, and that will be my C vector for the output matrix, while the D is same. And if I want to obtain the H for the observable matrix, I need to take the transpose of the C controllable canonical form. So this is how I actually write the observable canonical form, by taking the transpose of the respective elements matrix. Now comes the diagonal canonical form. If you have a characteristic equation obtained from the pulse transfer function and the roots are all real and distinct, then you can easily form the G matrix by placing those roots at the diagonal and keeping all the other entries as 0. This will give you the G matrix for the diagonal. Keep in mind, this formation only exists if you have the roots which are real and distinct poles. And if you want to formate the input matrix, you will just replace all those entries by 1. And if you want to obtain the output matrix, for that purpose you need to convert the impulse transfer function in the formation of a partial fraction, just like the A over given z plus pole 1 plus b over for the given z2 plus the pole. Those A and B coefficients are actually the values of the output vector matrix C, whereas the D is same as in the previous cases. You can also easily understood this whole scenario when we are going to solve the example in the upcoming slides. Now what is Jordan canonical form? If you have a pulse transfer function with multiple poles, that means the values of the poles are being repeated, then you will be able to form the structure in the same that is being formed over here. Now what you will be doing, that suppose that you have a pole P that is equal to 1, and the number of poles with the same values are actually 3. So what will you do? That first of all, you will place the value of pole at the diagonal, P1 that is 1, 1, and similarly 1 again. Now for the first entry, the P1, it will be placed directly. For the second repeating pole, there will be 1 in the previous entry in the same column. Similarly, if there is a P1 at the third place, it will be once again be having the 1 in the prior entry and 0 in the remaining form, and this will be go on repeating the same way. So this is the Jordan canonical form, and I hope so that you will be easily understanding if we solve the example regarding it. However, the C1 and C2 are same as that of the been discussed in the previous case, just by replacing the impulse transfer function and solving it in the form of by resolving into the partial fraction, and the values of C1 and C2 will be same as that of the values of A, B and C and so on. Now consider the example attached in this document. Now let us solve this example so that we can easily understand how to write the given impulse transfer function in different canonical forms. Suppose that we have a impulse transfer function defined by z plus 1 over z square plus 1.3 z plus 0.4, and we need to analyze all the canonical forms for the given system. Now we know that the general discrete time control system model is given by this equation xk plus 1, that's equal to g xk plus h u of k c xk and d u of k. We need to find the values of g, h, c and d. Now first of all, just write the general expression for the impulse transfer function defined by the b naught zn to the last bn coefficient divided by the zn plus a1 zn minus 1 till the last an coefficient. Now if you look into this example, what is the order of the system? This is the characteristic equation and the highest order is 2, that means the n is equal to 2. Okay, what will be the value of b naught from here? B naught is equal to 0, and if you look at it, that you will easily realize that zn is missing from this function, so b naught will be 0, b1 will be 1 and b2 will be 1. Similarly, the value of a's, coefficients of a's, a1 is equal to 1.3 and a2 is equal to 0.4. Now if you remember this controllable canonical form equation, generally it was written as, so first of all let's define the order of the matrix. Since n is equal to 2, so it will have 2 rows and 2 columns, and standardly defined by this equation, 0 and 1 and is the first row. Secondly, we will mention the value of a1 Alright, with the help of this general form, we can easily adjust the values of a1 and a2, which will be minus a1 which is 1.3 and minus a2 that will be minus 0.4, while the rest will be followed as the conventional way. 0 and 1 are the unit vector, which is telling us that the system has only one input. Similarly, we can also find out the values of the vector C matrix by taking help of this formation, where b naught was 0 and we have the value of bn, that was b of 2 and b of 1, that was given as the 1 and 1. So this is how we actually formed our canonical form. Similarly, I can find the observable canonical form by taking the transpose of the G controllable canonical form to get the G observable, and take the transpose of the H controllable matrix to get the output C matrix, and the observable H vector is equal to the transpose of the C controllable canonical matrix, and by doing so I get my desired observable canonical forms. Now lastly, the formation of the diagonal canonical form. For that purpose, I will expand my pulse transfer function into a and b coefficients, and by evaluating those a and b constants at the given poles, I will be able to find out the values of my diagonal canonical G matrix and the output matrix, which is equal to the 5 by 3 and minus 2 by 3, which is the value of C1 and C2, and the values of poles, Z is equal to minus 0.5 and Z is equal to minus 0.8, which is being represented P1 and P2 as it is being studied in the slides. Also, it is to be noted that our given system has all real and distinct poles. Therefore, we would not be able to form the Jordan canonical form at this point. However, I will be telling you the how to prepare the Jordan canonical form if we go through the non-uniqueness matrices till the next lecture. So this is the end of today's lecture. I hope so that you have understood a lot to this discussion, and if you are not able to understand any of the point, kindly do comment in the comment section. I will really appreciate if you do ask the questions. Thank you very much.